Hello. The topic of this video is advanced structures for roofs. But first, we are going to cover different connections between the timber pieces of simple roof structures. And then we are going to look at how we can design a gable roof structure. We will cover the suspended roofs and the advanced structures. Let's start with answering this question. How can we connect timber pieces? The first, we will look at the connection between a purlin and a rafter. I think you remember this example. Here we see a series of rafters, and they will be supported with this rich purlin. This is the section that we learned last week. Here we can see the purlin and one of these rafters. We don't want the rafter to slip downwards with the inclined position. And in order to support it, in order to create a nice connection between these two pieces, we can create a sort of groove by carving out this little part of the timber. That's the lower side of the timber, the rafter, and we can attach this little groove over the corner of the purlin. By this way, uh, the rafter will sit tightly on the corner of the purlin. That's what we call a groove. A stud and the purlin can be connected. Uh, Here we see the ridge purlin. It needs to be at this level. That means we need vertical pieces, which we call the stud, like this. If we create this type of end of the stud, uh, and obviously we need its counterpart on the purlin, we can create this little hole right underneath the surface, which we call again a groove, zıvana in Turkish. And that little piece can be called a tongue, lamba in Turkish, lamba zıvana birleşimi. Uh, that way, the stud will tightly be connected to the purlin. Also, additionally, we can use these L-shaped brackets, little thin steel pieces in the form of L letter, and we can use long bolts, uh, bulon in Turkish, and nut to secure it in the other end, somun in Turkish. Uh, by this way, we will be connecting the stud and the purlin very tightly. How about a bracing and the stud and a bracing and the purlin? I think you remember the main job of the purlins will be transferring the roof loads, all these rafters, the loads of all these rafters to the stud. Uh, and if we use bracings, that means the load transfer will be supported in a better way. All the loads will decrease with the help of these bracings here. That means we need to make connections between the purlin, the stud, and the bracing. Just imagine that we are looking at the system from the front. This is what we will see. First, we are going to see the stud here in the middle part. That's the stud. And if we create these type of grooves on this point here, then we can have nice places, nice surfaces for the bracing to be placed. With these grooves, the bracing will not slip downwards. And if we create these grooves on the bracing, then with these holes, we can drill that hole all through the bracings, the two bracings and the stud, and we can place this long bolt and secure it with the nut. That means we will be connecting the stud and the two bracings on its either end, on its either side, very tightly. And we can do a similar type of connection between the purlin and one of these bracings. Here, in this example, we see that, again, the upper side of the purlin will be carved out slightly. We don't want to carve it too much, too deep. That means if we do it like that, then we will be creating a weak point, weak spot for the purlin. And in its opposite direction, we can create the mirrored version of this groove on the bracing here. By this way, we will have a straight line which we can drill a hole so that we can place this long bolt and secure this nut tightly, like that. Uh, let's take a look at the same connection in the opposite side. It's the same thing. Here you can see it in a better way. We can just creating this little groove here up in the purlin, and right beneath it, the where the mm, bracing is being connected, we create a similar groove so that we can have this long hole drilled, which we are going to place the bolt, long bolt. Or instead of carving out all these pieces and trying to connect them with bolts, we can prefer a simpler way of connecting these pieces. I think, again, you remember this example from the last week's course. Here we see an intermediate purlin, and right underneath there's the stud, and in two sides, there are two bracings. Here you can see they use little pieces of timber to support the ends of the bracing. It's just nailed without using complicated systems like bolts or drilling holes. It's nailed right underneath a purlin, and it creates a support, a stopping point to prevent the bracing to spread sideways under the load of the roof. Uh, but how we can do the connection between a stud, a purlin, a rafter by using colors. Uh, Here we need colors to secure the system, to lock the system, uh, so that the whole roof structure will hold in a better way, especially against the lateral loads like wind or earthquake. Uh, we see the purlin, that's the purlin, and it's right above the stud. And the color will be connecting the stud, the purlin, and the rafter all together. We can use only one color on this side because there is this parapet wall. We don't need to tighten the system on the side of the wall. Or if there is this stud in the middle part of the roof, not on the side of the roof, but in the middle part of the roof, here there's this rafter, and we can use two pieces of colors, double colors, on either side of the stud. As you can see, the rafter is being connected to the stud and the purlin all together with the help of these double colors. Here in this perspective, you can see it in a better way. There is this purlin, the stud, and for the stud, you remember we need to prefer a piece with 10 centimeters to 10 centimeters square section. That's the minimum required sizes for a timber stud, single piece timber stud. And for the color, we can prefer a 4 centimeter thick pieces, timber pieces. Of course, these side, the end, that end needs to be shaped like this with the inclination of the rafter. and there's this rafter. In normal conditions, this is what we prefer for a single piece, timber piece of the rafter. It needs to be minimum 5 centimeters to 10 centimeters, and the total length can be 3 meters. But if the rafter is directly above the stud and we want the two colors to connect the rafter to the stud and the purlin, you can easily understand or imagine that if you prefer a 5 centimeter piece here, like this, it will be thinner. If this is 5 centimeters, and if that's 10 centimeters, there will be 2.5 centimeter gap here on the side and another gap in the same size on the other side. And we won't be able to connect the rafter to the stud using this type of colors. So that's why we need a 10 centimeter instead of a 5 centimeter rafter. We need a 10 centimeter rafter only here in this position so that we can connect the stud easily without leaving any gaps using these colors. Again, here we can drill the holes and use the bolts to connect all these pieces. Just imagine yourself, you are floating in midair looking downwards. You will be seeing the upper surface of the rafter, this 10 centimeter surface, and right underneath you will see the purlin like this. Uh, that's the 10 centimeter thing. That's the top view of this color, and this one here. That's the horizontal surface, upper surface, and then we are going to be seeing the inclined surface, the shaped surface. That dashed line will symbolize the position of the bolt, and this dashed thick plus sign will symbolize the stud. Because we won't be able to see the stud itself, it will be blocked with the rafter and the purlin. That's why we need that kind of symbolization. The same example, the purlin underneath, there's the stud and the colors right on its two sides. Okay, we covered the connections. Let's take a look how we can design the structure for a gable roof this time. We are going to learn the timber pieces and then we will proceed to the gable wall. That's the shed roof that we worked on, and that's the gable roof. Basically the same thing. The only main difference is the shed roof has inclined surface towards one direction, and that's it. And in the gable roof, we see two inclined surfaces on opposite directions. That's the rafter system. And this is the ridge purlin. Underneath, there is this stud so that all the loads can be transferred directly to the structural system. And we see a wall purlin here on the other end. That's the eave, and this is the ridge part. If we are going to create the gable roof, we can just imagine that we are mirroring the same system on each side. Uh, as you can see, it's a longer structural system for building the beams. There is one beam on this side, another beam, reinforced concrete beam on the other side, and we see a third beam in the middle direction. Mm, there is this rafter system, the same thing with the wall purlin and the ridge purlin, and the same system of rafters are mirrored towards the other side. There is this other eave here, one eave and the second eave. We are placing the wall purlin, the second wall purlin, the same ridge purlin here, and the same type of stud and the bracings and the colors and everything. Uh, there's this example of gable roof, two parapet walls on these sides. These are the exterior building's exterior walls, and they are just slightly higher than the inclined surface of the rafter. This is the ridge line, the sloping roof surface, and the other sloping roof surface. One eave, the first eave, and the second eave, two eaves on the other side. If you remove the structural system of the roof, the timber structural system of the roof, that's what we will be looking at. That's the reinforced concrete floor slab. We know that it's right underneath. There are beams, horizontal structures, and these are two gable walls. That means inside this gap, right over the reinforced concrete floor surface, first we can place our wall purlins like that, and that will be the ridge purlin. Uh, that distance is important here. If this distance is shorter than 4 meters, the total length of the ridge is shorter than 4 meters, that means we can have only one timber piece, and we can create the ridge purlin out of this one single piece, because this is the minimum required dimensions for a single timber piece. It needs to be at least 10 centimeters, the minimum size for this section, and the 12 centimeters, again, the minimum height for the section. The total length of the piece can be maximum 4 meters. That's why if this distance is under 4 meters, it's shorter than 4 meters, we can use one single timber piece, solid timber piece, for the ridge purlin. And of course, it needs to be at this level, high above the upper surface of the floor. We need studs on each end so that it will be supported. One stud on this end, another stud on this end, and one single timber piece of rafter if the distance is shorter than 4 meters. However, if it's longer than 4 meters, then it means that only one single timber piece will not be enough for us to create that ridge. We will be needing at least two timber pieces, and we need to connect them on this end here. One piece for the ridge purlin, a second piece, and they are connected here end to end, so that we will have a longer ridge, longer than 4 meters. That's the maximum distance. We can have shorter pieces like 2 meters, 3 meters, 3.5 meters. These are all okay. If we place studs like the previous example, then this end of this piece will be supported. However, the other end will be unsupported. The same thing for this other piece, this second piece. This end will be supported. The middle part won't be supported. That means the system will fail, fall down. That means we will be needing a third stud if the distance is longer than 4 meters, so that the end points of these two timber purlins will be supported with the studs. And we can connect them using not L-shaped steel brackets, but long steel sheets. We can drill the same type of holes so that we can bolt them together in this connection. Or instead of connecting them end to end like that, we can again carve the timber pieces, the ends of these timber pieces like this. It looks like some sort of dovetail connection. In Turkish, we call it kırlangıç kuyruğu geçme birleşim. And we can bolt the two purlins together like that. It will provide a more secure connection. And above the ridge purlin and the wall purlins, we can place rafters, and three of them will be right above the studs. And we can connect them with these colors, double colors in the middle part, only one color on this part because we don't need a color. There's this parapet wall on the other side. Here, if you focus on the connection of these two rafters like that, we can do, we can carve one of these rafters like this here. It's this timber piece carved out like that. And we will have another piece in the opposite direction. This time it will look like something like this. Okay. It will look something like this. The first piece, timber piece, will be carved out like that, and the other one, the opposite one, will be carved out like this. And you can drill the hole for the bolt, so that these pieces can be connected uh, in their center. Here, there is another perspective that we can understand the system in a better way. Instead of creating one single hole and using a big bolt, we can nail them together from many points. And we will be supporting the connection between the purlin and the stud using these bracings. Only one bracing if it's on the wall side, the two bracings in the middle stud. And this distance between these two rafters that connect the studs and the purlin together will be divided into a series of rafters. But how many of them are we going to use? I know that there is this gap. Let's say it's X centimeters. I can find out by dividing this X centimeters into 45. And when we do the calculation, we need the integer here, and that will give us the quantity of rafters. And the gap between these rafters can be approximately 45 centimeters. It can be 45.5, 48 centimeters, 49 centimeters. It doesn't matter. But the number of the quantity of the rafters obviously needs to be an integer. And these are the first series of rafters. We can do the same calculation if the distance between this rafter, this stud, and the other stud, we cannot see the stud because it's blocked with the gable wall here, but we know that there is this stud and there can be a different distance between these two studs. Let's call it y centimeters. Then we can do the same type of calculation. We need to divide it to 45 and get an integer as the quantity of these rafters. And the gap between these rafters, the other series, can be different. It doesn't necessarily have to be 48 centimeters. This time we can have maybe 46 or 46.8 centimeters. It doesn't matter. The gap between the rafters can be minimum 40 or 45 centimeters, and it shouldn't exceed 50 or 55 centimeters. We can have different alternatives. And let's take a look. What is the distance or the limits for this length? If the distance, this length of the roof is shorter than 3 meters, then it means that we will be using one single timber piece as the rafter. Only one single timber piece can create the rafter because for the rafter, one single solid timber piece, the dimensions should be minimum 5 centimeters to 10 centimeters. This is the minimum limit. We can have bigger ones, but we shouldn't have shorter ones. And the total length can be maximum 3 meters this time. It shouldn't exceed 3 meters. That's why if the distance is shorter than 3 meters, then we will be using this one single piece of timber. And we are going to place this one single piece of rafter over the purlin, ridge purlin, and the wall purlin. That means it will be supported on its both ends, on two ends. But if the distance will is larger than 3 meters, not shorter but longer than 3 meters, then we will be needing two pieces of timber to create the rafter. Uh, First piece will be like that. The second piece will be like this, and they are going to be connected in the middle part here. But if we use only one purlin and the one ridge purlin, this middle part will be unsupported, and the system will fail. They will fall down. That means we will be needing an additional purlin in the middle, which we call an intermediate purlin, so that the ends of these timber pieces, that piece will be supported on this end and on this end, on the other end. The second timber piece will be supported in a similar way, this end and in this end. And just like the ridge purlin, this intermediate purlin also needs to be supported by studs, obviously, and they need to be connected with bracings and collars, just like the ridge purlin. Here, I will place a stud, and depending on the total length, maybe another stud and a third stud, so that these rafters can be connected. And again, I will be using bracings and colors, double colors or one-sided colors, like that. Uh, that's how we can create the timber pieces of the gable roof structure. Let's take a look at the material and the construction technique for these gable walls. We know that there will be either reinforced concrete building structure on the floor or steel or timber building structure. And that's the floor surface. And right underneath the floor surface, there is this reinforced concrete beams. How we can create these triangular gable walls? We can have different alternatives. Here you see that there is this reinforced concrete building structure with columns and the beams, and that's the top floor. Right above that floor, they created this gable wall out of bricks. Placing the bricks on top of each other, they constructed this triangular wall, and the whole wall will be supported over the surface, or will be sitting on the surface of the floor, and the whole wall will be connected to the upper surface of the floor with a thin layer of cement mortar. And it's very weak. This connection is very weak. Due to lateral forces like earthquakes or winds, strong winds, there is this high risk of this whole triangular gable wall to be disconnected uh, and fall down and hurt people or the property like this. Here you see that there are gable walls made out of bricks, and the whole wall is only fixed over the upper surface of the floor with a thin layer of cement mortar. And I don't know what caused this failure, but most probably the loads of the roof, or maybe because of a strong wind, we see that the gable wall fall down. And obviously this, it looks like a school. Maybe there were students and they were hurt. Instead of uh, creating this gable wall out of bricks like that, we can either construct this gable wall out of reinforced concrete. That means this reinforced concrete building structure, beams, and the floors will be cast at the same time with the gable wall. There will be only one single object the whole gable wall and the building structure will be constructed uh, out of reinforced concrete. Or if you don't want to create a concrete wall altogether, then we can have the same structure. You see that there are building columns, the structural system of the columns, and there is this beam on the floor. And instead of stopping there, these columns, they continue upwards, and they are connected with these inclined reinforced concrete beams, which create some sort of frame. And inside this frame, they constructed the brick walls. That means the whole brick wall will be supported not only on this side over the reinforced concrete floor, it will be supported on four sides. It will be tightly connected to the reinforced concrete frame, and that will hold the wall. It won't fall down this time. Okay, the gable roof structure is being covered. Let's take a look at to the suspended roofs. What if there is not a floor available for load transfer? Here, in the load transferring roofs, all the rafters, purlins, and other components, studs, they create all these loads, and the whole load system, all the loads will be transferred directly to the structural system of the building. The purlin will transfer the loads to the stud, and the stud will transfer the loads to the structural system of the building, that beam here. These wall purlins will transfer the loads to the structural system, the reinforced concrete beams, like that. And the loads will be transferred to the columns and to the foundation and to the ground. That's why we call this type of roof the load transferring roofs, or oturtma çatı in Turkish. What if there is no floor, only a span, a gap? Here we see that there is this structural system, the building, another structural system building, but there is nothing else in between. There is only one single gap. And if you want to create a roof, that means there is no available surface for us to transfer the loads. Here we need to design a suspended roof. In Turkish, we call it asma çatı. And in order to create this suspended roof, we need a truss. This is called a truss. The simplest truss is a triangular combination framework made out of pieces. These pieces can be created out of timber or steel, something like that. And the simplest alternative is this. I use a piece, let's imagine that that's a timber piece like this, another one like that. I'm connecting them, and a third one like this. So I created a triangle out of these timber pieces, which I call a truss, or in Turkish, it's called makas. Makas. And I multiply these trusses in one direction, towards one direction, and place the wall purlins and the ridge purlin and the rafters over these trusses, so that the loads will be transferred to the truss, and each truss will transfer the loads to the supporting surfaces on its sides, like that. That's what we see right underneath. And that's the simplest truss, a triangle truss framework. And we can create complicated ones using other pieces. That's one of the trusses, another one here, another one. And as you can see, there's nothing here. It's just a span. However, on this side, there is this load-bearing surface, and on this side, another load-bearing surface. So the loads of the roof will be transferred to the truss, and this these trusses will transfer the loads towards the sides to the load-bearing surface of the building. In this example, most probably this is a traditional building, some old historical building, and these are masonry, stone masonry walls. All this surface here is a load-bearing masonry wall. Most probably there's another wall here, but instead of masonry walls, here on these ends, we can create reinforced concrete beams and reinforced concrete columns, the usual building structure that we learned uh, last semester. Uh, Okay, let's take a look at the truss, how we can create a truss and how it supports all these loads. There is a video without using any nails or bolts, just using some pieces or connecting them. He's creating some sort of truss. It's not in the usual form of triangle, but it supports his weight. And that's the truss uh, here. And above the truss, we place the wall purlin, another wall purlin on this end, and the ridge purlin. And above the purlins, we place our rafters, same rafters. And all the loads of the rafters and the above layers, obviously, the roof, all the loads of the roof will be transferred to the rafters, and the rafters, the purlins, sorry, the purlins will transfer the loads directly to the truss. Uh, in normal conditions, when we apply the loads over the truss, it can transfer the loads to these surfaces. But in normal conditions, the truss, these pieces of the truss, when we apply the loads, it wants to spread towards the sides under the weight of these rafters and purlins. Uh, and it will fail, it will fall down. However, if we use a third piece to connect these inclined pieces and to close the truss, that third piece will tie these inclined uh, pieces of the triangle towards the center, and it will prevent these pieces to spread sideways. That's why it's the simplest truss here, like that. And if we use a third piece, a vertical one, in the middle, then the loads will be collected towards the center and upwards with the help of this vertical fourth piece, and the loads will be transferred sideways to the structural system of the building. You can imagine a man bent down like that. His legs and his feet stood on the load-bearing uh, surfaces, but there is nothing in between. There is a gap in between. In normal conditions, these are the inclined pieces of the triangular truss, the upper inclined pieces of the triangular truss, his legs. In normal conditions, when we apply the loads, his legs wants to spread sideways and his back will fall down, descend down. However, if there is a third piece, a horizontal piece, which connects his legs together, that horizontal piece will prevent his legs to spread sideways and collect the loads towards the center. And you just imagine that he is holding that horizontal piece with his hands upwards. He's lifting the piece, the middle part of the piece, upwards like that. And that will create the fourth vertical piece like this. And the loads will be transferred upwards, and through these inclined pieces, the loads will be transferred to the structural system. secure load-bearing surfaces like that. Uh, okay, so that's the truss. And over the truss, we place, this is the truss, and 4 meters apart, we can, if we are creating a timber structure, there is this first truss, and there's a 4 meter gap in between them, a second truss here. That's the truss. And one of these trusses will be created at least using 4 pieces, 2 inclined pieces, which we call principal rafters. These are called this piece and that one is called principal rafters. Üst başlık in Turkish here. The third piece, the horizontal one that connects these principal rafters together, prevents them to spread sideways and collects the load towards the center. This third piece is called a tie beam, bırakma kirişi in Turkish. And there is this vertical one. It looks like a stud, but it's not. Uh, it's a different piece. We call it a post, baba in Turkish. What's the difference? In load transferring roofs, where there is an available roof floor surface here, reinforced concrete floor surface, you know that I place wall purlin here, another wall purlin here, and there will be studs here and here so that I can place a ridge purlin. And over the ridge purlin, we will have rafters. And we know that in load transferring roofs, the loads of the rafters will be transferred to the purlin, and the purlin, ridge purlin will transfer the loads downwards via these studs to the structural system of the building. However, in the truss system, in the suspended roof system, we learned that we can place the same wall purlin here, this one here, and the other wall purlin here over the trusses, and the ridge purlin here in the middle part, there. And over these purlins, we can place the rafters like this, like that. And the loads of the rafters will be transferred to purlins, and the purlins will transfer the loads to the truss. First, the principal rafters get the loads, and they want to spread sideways. However, the tie beam will connect them and transfer the loads, collect all the loads towards the center, and opposite to the studs, the posts, this vertical piece will collect the loads upwards, like this, upwards, and via these principal rafters, the loads will be transferred sideways to the structural system of the building. That's the main difference. In the previous version, load transferring roofs, load transferring roofs, the load transfer via studs is directed downwards. However, in the suspended roofs, the load transfer will be upwards in the post. That's the main difference. Okay, let's take a look at the same thing one more time. I have this truss created with these 4 pieces, 2 principal rafters, inclined rafters, 1 tie beam, horizontal one that connects them together, and one post uh, here in the middle, vertical. That's one of the trusses, and I can have another truss by leaving 4 meter gap in between. And over these trusses, I will be placing two wall purlins and one ridge purlin here. And over these purlins, the wall purlins and the ridge purlins, I will place a series of rafters, the same common rafters that we learned previously. Okay, let's take a look at the load transfer. All the roofing surfaces, insulations, roofing products, and all the loads of the rain, snow, birds, everything will be transferred to the common rafters. First, we have the common rafters. Including their own weight, all the loads will be transferred to the purlins, wall purlins, and ridge purlin, and the purlins will transfer their loads to the truss. First, principal rafters. Under the loads, the principal rafters wants to spread sideways and fail down. However, because we have the tie beam, it will collect all the loads towards the center, and then via post, the loads will be transferred upwards to the principal rafters one more time, and the principal rafters will transfer the load safely to the structural system of the building. That's the load transfer order in suspended roofs. For the roofs with basic geometrical forms and relatively small buildings like shed roofs, gable roofs, all our aim of creating these series of rafters and purlins, everything is to create this inclined surface. All the series of rafters will provide us to create this inclined roof surface so that we can place all the roofing products and the insulation layers and everything. That's why we do that. And if we want, instead of creating this simple roof structure, we can simply cast these inclined surfaces out of reinforced concrete. Here we learned last semester how we can create horizontal floors. They are supported with beams, horizontal beams, and each beam will be supported with these vertical columns like that. We can do the same thing, but not horizontally, but inclined, sloped way like that. The same type of reinforced concrete floor, 10 centimeter thick floor, the same type of reinforced concrete beams, not horizontal but inclined in this example, and they are right connected with the columns, vertical columns. Or we can use prefabricated panels. These can be cast out of concrete, but a special type of concrete because in normal conditions, normal concrete or reinforced concrete will be so heavy, and we don't want heavy objects for the roof. Instead of normal concrete, we can have autoclaved aerated concrete. That's a special type of concrete, or in short form, we can call it AHC. In Turkish, we call it gaz beton. It has many tiny voids, pores inside it. And by this way, we can have a very lightweight concrete like that. Okay, we covered the roofs, so suspended roofs. How can we design a roof for bigger spans and complicated forms? Here we need to learn advanced structures. For more complex geometries and bigger spans like elliptical paraboloid or hyperbolic paraboloid or spherical surfaces, these are huge. These can be tiny shapes or huge buildings, huge structures that cover a very vast area. We can either prefer advanced timber structures such as glue-laminated timber, or we can create a structure out of cables and membranes. We can have pneumatic structures or space frames. Let's take a look at the glue laminated timber, tutkallı tabakalı ahşap. Here we see our tree trunk and we can saw it into smaller pieces uh, like this, which we call a dimension lumber, kereste in Turkish. That middle part can be used as single solid uh, s- timber stud, maybe, and that piece can be used as a rafter or a purlin. But this is a single timber piece. And instead of using a single timber piece, because we have limits for the length obviously here. We can use many timber pieces and we can connect them together and glue them together to create bigger pieces, much bigger pieces. You see that three pieces with the annual rings directed in opposite ways. Uh, and we can create very large beams that can span above maybe 150 meters or 200 meters, like that. Uh, this is a huge timber uh, beam. In this example. Uh, it will be very useful because single solid timber pieces, they shrink. They will swell if they are placed in a humid environment. All the humidity, water in gas form in the air will be sucked into the voids of these timber pieces and they will deform. You remember that there are different types of deformations based on the location of these timber pieces on the tree trunk, based on the position of the pit. If I create a timber piece like this, once it swells or shrinks, it will deform uniformly. If the piece is located here, but it will deform in a bad way, and we don't want it because we want to prevent it because it will affect the load bearing capacity in a negative way. Uh, However, if we prefer glue laminated timber, here you can see that two neighbor pieces, their pit will be directed in the opposite direction, in the opposite way. This is the first piece. It has this pit here towards this direction. Another piece, its neighbor piece, but this time the pit will be in the opposite direction. That means the upper piece will want to swell like that, and the lower piece will want to deform in the opposite direction, and they will prevent each other from deforming in a bad way. There will be no risk of shrinkage anymore. We can prefer steel cables in order to suspend the surface of the roof or the slab of the roof like this. Here we have this example, a floor surface. It's a heavy surface, and we can use masts. These are called masts. They look like inclined posts, something, and we can connect them with cables, creating a tensile strength, so that the loads of the roof will be transferred to the ground use via these cable system. In Turkish we call it asma germe sistem. Asıyorum, asılmış ve gerilmiş. Çelik kablolarla gerilmiş. All the loads of the roof will be transferred to the ground via these cable structures. This is an interesting example. It's a paper factory. Uh, when you first take a look at the building, it looks like a bridge, not a building, but a bridge. But here you can see the building. It's here. In normal conditions, we start the construction from the lower end. First, we construct the foundations and then we proceed our way upwards, uh, constructing the structure of the building, and the roof will be the last to be constructed. However, in this example, they first created the roof. The roof is suspended uh, to these posts, large posts with these cables, and underneath the roof surface, they placed the whole factory building. They first constructed the roof and then uh, constructed the building underneath the roof. Instead of heavy roof surfaces, we can use membranes, örtü. These are created out of plastic or some sort of fabric, and they are hanged in between these posts, steel posts, masts here, with these cables. You can see the cables like this. Pneumatic structures is air-inflated plastic surfaces. Şişme yapılar, şişirilerek oluşturulan yapılar. There are two main types. In the first one, we have only one layer of plastic surface, and we inflate the whole plastic surface by feeding air constantly. It inflates like a balloon, but we need to keep feeding the air all the time. Otherwise, the whole system will deflate. Uh, this is the air-supported type, and we can have a pre-inflated structure. We don't need to keep feeding the air constantly. We can just place this whole structure over an area to create the space. This is called air-inflated. Space frames, we learned this is the truss, düzlem, kafes, makas. In order to create the roof, here we have space like this. This is our building, and we want to have this span like that. That's why we prefer these trusses. Over this gap, we place one of the truss, and 4 meters apart, if it's timber, obviously, another truss. 4 meters apart, a third truss, and the fourth truss, like this, so that we can create our purlins and rafters over these trusses. And if I want, instead of a building like that, I can enlarge the building in the side towards this direction and create a bigger building like this by placing more trusses in this direction. I will be able to enlarge the building in one direction. However, I cannot be doing the same thing, same enlargement in the other direction. This is not possible. It's limited with the truss. However, in this direction, I can go as long as I want. What if, okay, that's the available direction for enlarging the space, but this is limited. I cannot do the same in the other direction. What do I need to enlarge the space in two directions, not only one direction, but in two directions? Then instead of a truss, düzlem kafes, we can use a space frame, uzay kafes. And it is created with these steel pieces. These are steel tubes, lightweight steel tubes, and this is the main part of this space frame, so that by connecting these steel tubes, screwing them, the ends are created like bolts, so that we can connect all these steel tubes all together using these connection points. That's one of the pieces. I can enlarge the space towards this direction and towards the other direction, towards the both directions, and cover a larger area. I think you all know this building. This is the intercity bus terminal of Antalya. Here you can see there's this roof like that, and right underneath, if we look above, that's what we are going to see. It's created with steel space frames, and the building can be enlarged towards this direction and towards this direction. Uh, Here we can see that they used columns here and a series of columns here. And in between, there is a huge gap, huge span that will protect people, cars, and everybody, everything from rain or sun. That's the space frame. And if we want, we can have a horizontal structure, roof structure like this, or we can create domes or vaults like this, or amorphous shapes. And you remember this is the Hyder Aliyev Center uh, designed by Zaha Hadid. Here we see this curved surface, a shell. Uh, Created with these white covering panels. And if we remove these covering panels, uh, right underneath, there is this space frame that creates that curved surface. And that steel space frame is connected to the main structural system of the building. This is the reinforced concrete. It looks like reinforced concrete structural system of the building. Okay, we covered the advanced structures. Hopefully, next time we will be looking at how we can provide insulation and roofing. See you.